In this video, we're going to be checking to see if a couple of different subsets of R3 will qualify as a subspace of R3. So for our first example, we're going to be taking a look at the set of all vectors such that the sum of the three components of the vector is equal to 0. So some examples of vectors that would lie within this set. We could do something like 2, negative 2, 0, since the sum of all three would be equal to 0. We could do something like 1, negative 4, 3, since the sum of all three entries is still equal to 0. Or we could do something like, 2, and then 18, and then negative 20. Basically, whatever you choose for the first two entries is going to dictate what your last entry necessarily has to be. Now, with that in mind, the three things that we want to show is that this set is non-empty. That is, we'll show it contains the 0 vector. So this would be considered axiom A4. So first thing we want to do is show that the 0 vector is an element of, we have yet to give this thing a name, so let's call it S for space, or subset, or subspace, or vectors. There we go, yeah, vectors. Now, 0 vector in R3 is going to be equal to the vector 0, 0, 0. And we can observe that if we take 0 plus 0 plus 0, which is the sum of the three entries, we do in fact get the 0 that we are supposed to get. Therefore, the 0 vector is contained within the set S. Now, for the second axiom, axiom A1, we are going to have to assume that there are two vectors within the set and show that the sum of the vectors is in the set. So we'll say let U and V be elements of S, and we'll let the components of U be U1, U2, and U3. That'll be equal to 0, and the components of V will be V1, V2, V3, and those will be equal to 0 as well. So vector U plus vector V would be equal to the vector U1 plus V1, U2 plus V2, and U3 plus V3. Then we can point out, same thing, or similar to what we did just a moment ago, we'll take the sum of the three components, U1 plus V1, plus U2 plus V2, plus U3 plus V3. Then we can do a little bit of reordering using the commutativity and associativity of the sum of real numbers. We'll point out that this would be U1 plus U2 plus U3 plus V1 plus V2 plus V3. But the assumption that we were making is that the sum of the components of U and the sum of the components of V would both be equal to 0. Therefore, this is going to be equal to 0 plus 0, which is equal to 0. Therefore, the set is closed under the operation of vector addition. Next up, we'll need to show that this is closed under scalar multiplication. So we'll take C times either one of these vectors. We'll do V. So this will be C times the vector V1, V2, V3. And we want to show that the sum of the components of this would be equal to 0 as well. So according to the definition of scalar multiplication in R3, this is going to be C times V1, comma, C times V2, comma, C times V3. Then let's check to see if it satisfies the given property. So the thing that we would point out is that if we take the sum of these three components, that we would get, let's see, I suppose we could factor out the greatest common factor of C and be left with V1 plus V2 plus V3. And according to the assumption that we made not too long ago, the sum of those three components should be equal to 0. We wind up with C times 0, which necessarily has to be equal to 0, since anything times 0 should be 0. So because we were able to show that all three of these axioms are satisfied, we can say, therefore, S is a subspace of R3. Now, to draw a parallel between this and Calc 3, this would also be considered the equation of a plane with normal vector 1, 1, 1 passing through the origin. So this is something that would split Euclidean space into say a positive side and a negative side. Now, I do want to have us try out one more. And the one more that I want to have us try out is determine if the following is a subspace of R3. And this will be the set of all vectors. We'll say S equals the set of all vectors W1, W2, W3 such that the product of all three components is equal to 0. However, using the zero factor property, this allows us to make a stronger statement. Either W1 is equal to 0, or W2 is equal to 0, or W3 is equal to 0. So what this is saying is this is the set of all vectors in R3 such that at least one of the components is equal to 0. I think that we can show relatively easily that the 0 vector is in the set and that the scalar multiplication, it would be closed under that operation. However, I fear for A1 because we don't necessarily have to have that 0 component in the same position. We could say, for example, let U be equal to the vector 1, 1, 0, which is in S, since 1 times 1 times 0 is in fact 0. We could say let V be equal to the vector, 0, 2, 4, which would also be in S, since the product of these three components is equal to 0. However, if we point out what U plus V is equal to by adding the corresponding components, we would get 1, 3, 4. The product of those three is not equal to 0, therefore this vector is not in S. As such, S is not closed under vector addition, so we can say therefore S is not closed under vector addition. So S is not a subspace of R3. For the connection into Calc 3, this would describe the set of all vectors whose terminal point is on one of the three coordinate planes, which guarantee in the xy plane, z component is 0, in the xz plane, the y component is 0, and in the yz plane, the x component is 0. Adding two of those vectors together does not guarantee that it will stay within the coordinate planes.